And thank you for joining us today. It is our great honor to introduce our speaker, Dr. Ava Chen, who is a postdoctoral scholar at Stanford University, advised by Alison Okamura. Her research focuses on design and use of wearable robots for the hand. She's interested in making the partially observable, partially controllable human-robot behaviors more interpretable to each other via sensory feedback. And she just received her PhD from Columbia University, advised by Matei. And before the PhD, she was a research assistant at Harvard University, where she studied jumping spider locomotion and behavior with Paul Shambo. And she received her Bachelor of Science in Mechie from MIT, where she contributed to the robotic socket measurement devices with author Petrol and Hugh. She was a 2023 and to 2025 NIHF 3-1 Fellow and 2024 ISS Pioneer. So let's join me in welcome Dr. Ava Chen for giving this exciting talk today.
Well, the honor is definitely mine. Thank you, Kenny, for the invitation. Thank you, Ava, for reaching out, also hosting. I'm really excited. This is a talk that will include some very new stuff and very old stuff. This talk is not going to be on my actual main line of research, which is on exoskeletons and haptic devices. For that, moving that to the seminar stuff, I'm taking this opportunity to talk about something that's really near and dear to my heart, and I haven't given talks about the spider portion of it since 2018, so I'm pretty excited. I think this is the seminar time. Yes, great, awesome. Okay, so we won't talk about exoskeletons or wearables. Instead, we're going to talk about just general ideas about dexterity. I'm hoping actually to learn from you, Dexlab. To get started, autonomous locomotion, and I include loco and manipulation here because the current state of robotic hardware and robotic software has gotten to the point where this is a video from May from the Robotics AI Institute, where what's normally a head is making contact with this medicine ball. That's the sort of front panel here. You have the arm, and you also have a leg, all working together to do a manipulation task that you would normally think is a dexterous hand. And then this is a result from, on the right, from physical intelligence on a very long horizon task of making what is apparently an acceptably tasting espresso drink. And what's involved there is you need to have these bimanual manipulators, grasping objects that are of real life textures, real life frictions, putting this tool into a fixture, putting in force, having it not slip, doing all these things. And so the current state of robotics is really exciting to be in. But still, we have a lot to learn from biological systems, and especially humans, which we've always considered as the pinnacle of dexterity. Here is a guy with 0.5 arms changing a bike tire. And I don't know if you've ever changed a bike tire, but he does this in 5 minutes. I do it in maybe 30 minutes. And so the dexterity involved here is, okay, you have toes, which my toes are not nearly as dexterous. You have the use of hands, you have the use of many contact surfaces. And playing, oh no, I paused it. This is a video of a spider hunting and collecting a mealworm that is around the same mass as it is and almost the same size as it is, and managing significant interaction forces while also maintaining uprightness. So biological systems are really cool. Why am I bringing up these topics? I'm sort of interested in the general idea of, like, how do we study dexterity? This is your just classic perception action loop of you have components that are externally observable. The perception side, you can consider your sensors. If you're a human, you have your 5 senses. And then you also have the actions of what is the person actually doing. So if I'm observing this scene and I'm looking at this person squeezing lemons, I can use my senses of my vision, of course, but then also an expectation of history, and make predictions on at what point is the juice going to stop being squeezed, at what point is the lemon dry, if no more juice is coming out, is it because our lemon is too unripe and there's not going to be very much juice in it, or are we done with the task? All of these things. What's interesting about the prediction and the observation side is it's very experiential and it's embodiment specific. I don't have it on the slide, but there's a interesting blog post from, I think, Rodney Books from a month ago on why is it that LLMs, why do they spit out such colorful prose? They're always describing scenes like the smell of something unintelligible, the smell of gray or something, where when humans write like very colorful prose, it's talking about drawing from senses and drawing from experiences. There's a quote of describing the looking out on the ocean scene and described as a plateful of sky because it's reflected as sky. How do we get robots to interpret actions and perceptions to make experiences? When we think about predictions and observations, there are some techniques that are in play. We can think about predictions as mass segmentation. We can think about long horizon learning. We can think about learning from history. And in terms of observations, we can use architecture design to try to direct attention to things we might care about, correspondences we might care about. And there's also a lot of work in learning and your lab, I think, knows much more about these than I do, not being a learning person. But the thing I'm excited about is, well, how should we set up experiments to extract variables that we can't directly sense and study or learn from systems where we can't ask the spider what it's paying attention to, and how we can't ask the robot what it's paying attention to. So how do we set up experiments to study these things? Okay. So as I hinted to, I'm going to talk about very old stuff and very new stuff. For spiders, I'm going to talk about this kind of spider. It's called Salticus scenicus. It jumps around, and talk about how it uses perception and manipulates the silk to get around in the world. For the new stuff, we have this experiment where we're using imitation learning to observe how humans change behavior with access to different kinds of sensory feedback. And I have an open question for you that's sort of interwoven in this talk, where I don't have any answers, I only have questions. I'm interested in, well, how do you study cross-embodiment observations? How do you get predictions? How do you get observations from systems that you can't directly ask them? So how do we encode, and if we're trying to train a robot system, how do we figure out what's important? How do we figure out if the system's paying attention to what's important? And what even is useful data? This is a very broad question. Okay, so let's get into spiders. What are jumping spiders? This is a jumping spider. There are many of them. The biological family is Salticids. A spider, of course, is a creature that is not an insect. It's an arthropod. It's those things that normally show up in every science article around Halloween because they're kind of scary. These guys, I think, are kind of cute. They are small. They live basically all over every single continent except for Antarctica, but someday. You rarely ever see them out and about because they're active hunters. They don't make webs. They will hide around and eat all the mosquitoes in your house. Spiders have 8 legs, 8 eyes. These ones don't make webs, but they make silk. And the kinds of spiders that we're going to talk about in this talk are around 5 millimeters big. They're tiny creatures. These guys navigate a 3D environment. They will jump from leaf to leaf. The leaves, of course, move in the wind. They're very small. So they're doing very complex 3D locomotion and navigation and path planning and reasoning. How do spiders make these jumps? So a spider has two parts. It has a head and an abdomen. And you can sort of think of the head as basically all brain with some legs and muscles. And then its abdomen is a fluid chamber. You can sort of think of it as, well, I'm going to describe it as a hamburger because it has muscles, but those are for flexing the legs. To extend and make a jump, this is hydraulically powered. So it squeezes its brain too. And all that fluid pressure extends the legs and generates quite a bit of force in order to launch itself. Spiders are active hunters. They will run around, they will find a piece of prey, and they will navigate to it. So they will make jumps multiple body lengths their size, and they will hit their target 90% of the time. They almost never miss. We're going to see a lot of slow-mo videos like this. Why are spiders interesting? Why am I talking about spiders for a Dex Lab talk? One of the popular ideas for robot learning currently is about how much data do you need? How do we scale learning? And what can we draw from the LLM world, from the natural language world? This is a screenshot I took from attending RSS 2024. This is Chelsea Finn talking about how much data, 3.6 trillion tokens was in 2024. It's only expanded since then for natural language processing. How much internet data is used to train these models. And if we were to use similar amounts of data for robotics, where you need physical examples, physical trials, we would have to increase the size of data by an astronomical amount, many trillions. Learning robotics is harder because you need multiple sensory modalities. You need a physical example. Yes, you can learn from sim, but you need to incorporate many aspects of physics that some of them are hard to model, some of them are weird and out of context. And if you don't already have the example, how do you provide it? But LLMs have gotten really, really big. Here is a chart of throughout time how many parameters there are in a general model. And for context, humans have around 100 billion neurons. Of course, a parameter is more akin to maybe what a synapse connection is between these neurons. So there's some argument on whether we've achieved human level brains, I guess. But still, it's quite a bit. So we take humans and we ask how many neurons are in a brain. Humans have a lot of brain. Cats, smaller, but still a lot of cognitive thinking. And then, of course, as the scale gets smaller, the number of neurons gets smaller. Spiders, you can count the neurons in their brains. They have very small brains. The brain is, for visual learners, the brain in a spider is the size of one poppy seed. So what are the spiders doing with their brains? Almost all of the brain space is devoted to retinas. Around 50–60% of the entire nervous tissue is just processing image data. So to make some comparisons of how spiders see, here's a top-down view of a person's head. Here's a nose, ears. Here's a top-down view of a spider. Front view of a spider. Spiders have 8 eyes. So a human, we have 2 eyes. And the green, we have some area of focus, what we're paying attention to. Then we have stereoscopic vision, but we also have some peripheral vision. And we'll pay attention to it in terms of, is there contrast, is there movement, big animal predators. Spiders have 8 eyes, as I mentioned. Two of them are the high focus, high resolution vision, and then you get some amount of attention from the rest of the eyes that are not quite as good. But a lot of the visual area is devoted to peripheral vision, and that's just focused on movement. It turns out that spiders can almost see all the way behind them, and they can also see a little bit above them as well. So what are they doing with all these cameras? Spiders do have a lot of reasoning. It's not just jump, attack, and movement. These are examples from a paper from my former advisor's lab, although I was not on this work, which I'm very unfortunate about because it's really exciting. Spiders are, in video game terms, glass cannons. They will run around and they'll attack things, but they're also squishy and they're small, and so they will run away from things that are likely to attack them. They don't have the hard shells or exoskeletons of, say, insects, and so they are also solitary, and so they will run away. So when a spider is looking at a scene and is trying to decide, is this thing worth exploring, or is this thing scary? This is a 3D printed blob. Where did you go? Where's my bee? Ooh. I'm going to skip ahead in this one. Okay. So the spider's looking around the scene. We've set up this experiment so that spiders will get really bored if they fully explore the scene, and they'll see what is left to look at. And so the spider decides that this is not a threat. In this work, we compared some, this is a pinned down dead version of a real spider, which is a predator. I thought I had cut these videos shorter, but that's not true. Okay. Mm. As you might have noticed, is very fast on my plate again, but it decided to just leave and exit. They have spider silk on the end, so they are bungee jumping away from danger.
So how far can a spider see?
How far can a spider
It
see?
seems it cannot see from the very right of the thing.
I don't have these slides, but the high resolution view is around a 10-degree cone, and they can definitely see the spider. All right. So we compare this in this work. They compared this to 3D printed versions, and see if I can advance it. And definitely there are aspects of features that they're paying attention to of whether something is scary or not. The work then continues to do an ablation study of, is it eyes? Is it legs? Is it just size? And it ends up being that it's not just a single feature. They end up making like these wacky nightmare spider monsters. So it's a compilation of, you can trick spiders to decide whether something is scary or not scary. But the conclusion I want to make from this is spiders are reasoning about the world. They are actively looking at a scene. So some brain space is devoted to reasoning, some brain space is devoted to processing. And you might ask the question, well, how much of that is your experience? This seems to be innate. Baby spiders, so having just emerged, they will recognize the difference between blob and scary. It's very fascinating. This that I actually worked on was jumping, so I'm going to force you to watch some jumping videos. Spiders do a lot of 3D navigation. This is a high-speed video. The playback is 2,500 frames per second. These spiders will jump at almost a meter per second in velocity. So we had to set up this crazy thing of high-speed cameras, a laser trigger to actually start tracking. We're illuminating the silk with a laser light. And in this case, the gap is 2 centimeters. At some point, around, so this is around 3 to 4 times their body length. Spiders will recognize when a gap is too far to feasibly jump, and they will just avoid it. So from this, if we make everything else too far away, they will always jump this gap when they get bored. Here's what that setup looks like. We have these platforms way high up in the air so that nothing else is interesting close to it. We have view, there's a top camera up top, laser light going illuminating the silk. And then these 2 platforms are on piezoelectric drives, and I will get to why that matters in a little bit. So spiders are willing to jump at different distances. And paying attention to how their launch sequence works. First, they're aiming. They're aiming with their legs to sort of estimate angle and distance. And these videos are not made as quick as I wanted them to. And so almost all of the launching power is from the back set of legs. Okay. So we're sort of curious at how jumps vary at different distances.
This seems really accurate.
Yeah, they
It's just
almost never miss. We'll get to what they're doing. You might have noticed the laser illuminated silk lines at the back. We're sort of curious what is happening with the jumps and why they're so accurate, and 2, what do the jumps look like. This is a comparison of a ballistic trajectory of if there's no silk and you're just considering their starting velocities, their joint velocities, just imagine abstracting their 2 body parts to be a hinge, and forwards what a ballistic version of their center of mass might look like, compared to tracking of this actual center of mass. You might notice that this is weird, and also overall it's a flatter trajectory than the ballistic one. So spiders are using their silk to reorient themselves in the air. This is a photo compilation of what is happening here. They're jumping, and without an influence of silk, they would be pitching up this way, but actually they land this way. Something that we were interested in is the spider eyes, the way they're positioned. They can see above them, they can see ahead of them, they can't see below them. That's where the So somewhere in here, the spider is deciding when to yank on the silk without looking. And so part of this work was trying to understand, is it within a reasonable reaction time for the spider to just do this closed loop, or is it a aim, fire, and then at some time pre-programmed open loop behavior? We did not actually get to the answer to this question, but we learned a lot of other stuff along the way. So we can think about the spider system as like a tube-link system, where when you're in the air, you're under some amount of influences. You're not so small that Reynolds numbers really matter all that much. So you can do a lot of inverse dynamics estimation. And something we're interested in is, when are we estimating that that spider is putting tension on that silk line? And these are very noisy signals, but a lot of it is near the end, and some guess of mid-jump spiders are yanking on the silk. So what if we deleted the silk? We had our high-speed platforms put slash into the silk.
Oh,
So two things to note here. One is that we can make the spiders miss almost all the time now. But also missing isn't that critical because the spiders, I don't know if any of you rock climb, but it's very frustrating watching the spiders. They basically have talons at the end of their legs, and any one of the legs can hold their entire body weight and moment from a single point. So getting them to actually completely fail is really hard. So summarizing here, small spider brains can do a whole lot. They're doing 3D path planning, navigation, object recognition, differentiating between scary things and food and boring things. And they're doing fast mid-air reorientation. So thinking about this open discussion question, making this an interactive session. So all that retinal camera processing is basically being distilled into positional velocity contrast with a little bit of feature attention. And I've been thinking about how robot camera visions and computer processing, almost all the time you're downsampling your camera information and your scene information and then feeding that directly into the model. But is that the way we want to do it? Or do we want to do some pre-encoding, I guess, some situational pre-encoding of not paying attention, discarding camera information when you decided it's not useful to the task, and then feeding in the full raw information when you're doing something like visually important.
thoughts.
I
want to let the students to talk.
Yeah, you didn't know this was going to be an interactive seminar.
Yeah, I think that's the case for spiders. Since from the experiment before it first came to the platform that just came to the platform, it does not focus on the larger spider, so it does not show some scale behavior at the first time, but when it focus on some scale, maybe I'm not sure if that video is shot in a very high speed camera, but it seems the spider needs some time to react and get focus.
The static recognition videos are all shot real time. It's not a high speed video.
Oh yeah.
But yeah, these are open questions. I have no answers. I only have questions.
Any other thoughts from students? Do I so that you?
Yeah, I think it's a really good question because I never think about this. Yeah, I feel like we usually, in my previous thinking, I think we need to have all information and make a decision, right? So but right now I've changed my thought. I think spider webs.
Yeah. Oh, 50,000 neurons can do so much. It's kind of infuriating. They're like really small.
Cody and
I think maybe it could deal with a little bit of failure modes because, like you said, the spider is very robust. Even if it makes a mistake, it's able to kind of, with one hand, kind of, or one arm, correct itself. I'm not sure our current hardware capabilities allow a robot, once it's steered away from that path, to like get back on track in a way. I think it may be kind of correlated with our hardware and I guess a little bit of our correction algorithm.
Yeah, I agree. I think certainly in the jumping aspect, I don't have any videos for this, but in the jumping aspects, the spiders are very bold. There's a little bit of weighing cost. So they do have some incentive to land perfectly and get to the right place that they want to be. But you're right, the stakes are not critical, whereas perhaps in most robot manipulation rollouts, you drop the object, the person telling you what to do stops the trial and calls it a failure. So then it's a little bit hard to I guess have low stakes learning. Although I think physical intelligence came out with some white paper on learning from failures. But I haven't really delved into it.
So I feel like this is also like a system problem, right? So I think first of all, like biological like sensors, they're like very different. Many animals, they're like evolved to have the ability to pick up, like for example, very high speed events. Like me, my ability, although I have like much more neurons than my cats, but I wouldn't be able to pick up these like very high speed motions than my cats. And so I think the first thing is about like the sensors capability. And the second thing is, what was the second thing else? Oh, I think there's also like this adaptive like attention on the events that's kind of like situational and based on the context. I think yesterday we actually have Oliver Cromer coming to give a talk, and in the QA session, he also mentioned about, okay, if you put your hands on a surface for too long, you will start to pay less attention to this like contact surface. So I think there's definitely some like kind of adaptive behavior on like even just on the sensing side. And the third thing is that I do think there is something pre-encoded in on the motion and on the like adaptiveness and the recovery of motion. Like what the spider did, we cannot do that. And what my cats did was, I mean, all these like fast movements and capturing all these like capturing the prey, capturing the birds. It's not what we could do, but we could do something different than them. So yeah, I think to me, these are the 3 points I could think of. Yeah, about this. Yeah.
And I think this question actually reminds me of a sensor I've used before called event camera. So this is a question like, do we really need a RGB images, or we should only focusing on the movement? So event camera actually don't give us the RGB value. It only monitors brightness changes of each pixel asynchronously. So they can support very high sampling rate and HDR range. And I've seen many people use it to capture high moving balls, or using a dog to capture tennis balls. So it also reminds me like maybe we can find an efficient way to not process all the RGB images. We only need to focusing on the movement, the core part of the scene. And I think this also happens to human eyes, because the motivation to design even camera is quite similar to our eyes. So if we look at the wall for a while, actually without any eye movement, the background would fade away. So we need some adjustment in our eyeball so that we can recapture the scene. So this is the principle to design the event camera. They only capture the changes, either through movement or brightness changes. So I think it reminds me of that. And I think that's also a direction that we can try to change the sensor.
Oh, yeah, that's really interesting, because when I think about sensor fusion, usually I think about two cameras to get stereoscopic views, and they're perform different roles. And then the rest of it would be different sensing modalities. But the spiders have 8 eyes, so maybe we just need more cameras.
I think the
More
autonomous driving
resolution.
cars, they have like many cameras.
Yeah. Huh. Yeah. Cool. Are we finished with spiders? I think we might be finished with spiders. The next thing I want to talk about is human sensory strategies and human redundancy. So this is a screenshot from Ariana Grande in one of those Vogue like "What's in My Bag" series. And here she's reaching into her bag, and I have a question for you. It's a leading question. Is she going to pull out the object looking at it? Is she going to like look to see what's in her bag, or is she just going to like yank it out. Pulling around the room. Votes for looking. Votes for no looking.
No.
Okay, she looks every time, and that was kind of frustrating because I wanted to find a clip of her just like grabbing it, but no, she looks every time. But the point is that both were possible. Humans have many high fidelity forms of sensing. You could use touch and recognize what's in your bag. You could use vision, recognize what's in your bag. And I think this is really interesting because there are a lot of examples of using teleoperation to do imitation, collect demonstrations for imitation learning. And one frustration, although people are working on it, is you can equip tactile sensors, and the tactile sensor community really wants to put their sensors on robots to do all sorts of things because humans have really good tactile sensing. We should learn from humans. You supply RGB vision, you supply tactile information, and then you use the online execution. And the robots don't use the tactile sensing data, even if they have them. That's not universally true. There are counterexamples. And my thought about this, so this is an example of mobile Aloha doing all these really complicated, really impressive tasks. Mobile Aloha does not use tactile sensing for any of them. It's just vision. My thought thinking about this is, well, if the human demonstration, usually you're teleoperating a system, and yeah, the human has some tactile information from using the gripper, using the operating system. But that's not, whatever the human's feeling is not conveyed to the robot. And also, if the human is teleoperating the robot, the human has different sensing modalities, and you don't get the same tactile feelings using your own hands. So if the demonstrator isn't really using the same tactile sensing as the robot does to perform a task successfully, why would this be conveyed as a lesson to the robot? If you haven't seen this particular video yet, I guarantee you will see it all the time. This is a demonstration from, I think it's 1996. There's a person striking a match, and then what they do is they anesthetize the hand, and you have this person struggle to pick up the match, strike it. It's getting cold in Duke, I noticed, so I think you'll recognize this yourself of when your hands are really cold and maybe you're wearing mittens, it becomes much harder to use your tactile feedback and perform tasks. You might be more clumsy than usual. Usually the clip ends around before the person succeeds, so I wanted to show the whole thing. And the point I want to make is humans struggle when they're used to using a certain sensing modality, but eventually you figure it out. Eventually you make do. Some recent work out of Allison's lab that I wasn't involved in, but in this demonstration, this is with the Everyday Robots group that I guess is folded into something else. What is happening is the human operator is providing demonstrations for the system, and the goal is to open the door. And what is required to open the door is you need to provide a certain amount of force. You need to provide make sure that your gripper doesn't slip against this door latch. They tried doors that swing on the left versus swing on the right, and all these things. And what's interesting is they did two conditions. In version 1, the person just provided a demonstration, it's all visual. In another condition, the humans given tactile sensing. And Alice's lab is all about haptic feedback and all this stuff. So the human is getting some pressure information. What is interesting about this work is none of that is fed into the robot. And the conclusion from this work in transactions haptics is that the task performance improves when the human gets haptic feedback. And one question is, well, I guess they're providing higher quality demonstrations in their behavior, even though the actual sensing is not conveyed to the robot. But we're confused why we're not giving the robot any form of, or the same form of tactile sensing if you're giving a human tactile sensing. So this is motivating very, very recent work. It's not even in progress. Don't worry about that. I'm going to present the work from a ridiculous mentoring crowd. There are more mentors coming in. Kosova is the more senior postdoc in Allison's lab, and she's running a user study with Aaliyah Smith from Monroe Kennedy's lab, and Alana is an undergrad on this project, where they want to know how task demonstration benefits from people given haptic feedback and people not giving haptic feedback from novices doing a self-operation task. I'll get into that in a little bit. What I'm talking about is, well, we saw this user study, and this is Sarah Klopsky, who's a first-year PhD student, talk about her work today. Well, if we have data sets involving human demonstrators that have access to different sensing modalities, can we train a policy using this and then use the policy to observe how the behaviors are, how the different data sets inform different adaptation behaviors? So what does a robot pay attention to if trained on different data sets? Okay. That was a really convoluted way to say what is happening here. So the task is very simple. There's a person wearing a HoloLens camera, and I will play this again. Wearing a HoloLens camera to get hand pose. And the hand pose is connected to the kinematics commands for this Canoa arm. Right, so operator wearing a headset, you get hand pose out of this. They're wearing a haptic glove. I will get at that in a moment. And the person can see the task view. The goal is to take this happy sack and move it from a start position to a goal state, which is on a piece of tape. And what is important about this work is the human and the robot have the same pressure sensors and feedback, I guess. Feedback to the human and pressure data for the robot. How we're doing this is this device. These are fabric tactors. So this is a pneumatic system, and we're basically using one of them as an actuator and one of them as a sensor. So if you press on one, and let's say that this is the robot one, you can convey that same pressure feeling to the human, one-to-one correspondence. We're very excited about this. So again, what's going on here? What we're considering a trial is the person maneuvering the Canova arm to approach the hacky sack. Our start time is when contact. We're using the pressure data from the pneumatic tactile sensor. And then we're watching the person lift up the object and release. People are imperfect and they're not experts at teleoperating, so we get lots of different diverse behaviors. What the data set consists of is one third view camera. We have the kinematics from the Canova arm. We have gripper width, and then we have pressure. For this, we're borrowing Truro Pen, who's from Sharon Song's lab, and so for that, we're taking advantage of diffusion policy because that's what they're doing. That's just it was convenient, and we have the expertise in-house. Why not? So these all go into the diffusion policy, and then what we're spitting out as actions is what the Canova arm should do next. Should it close the gripper? Should it open the gripper? And then where to move that end effector. Okay. This is data from 2 participants. I told you it was really early work. And the same 2 participants with haptics, without haptics. The scale is time since contact against the object, and the trial ends when the person drops the when the object hits the goal state, which usually, because it's a human teleoperator, the arm is somewhere in the air and you let gravity do the work. This is the from start state to end state, where the horizontal position is, where the vertical position is of the end effector. here is the gripper width, although it's inverted, so 0 is closed, or sorry, 0 is open, 1 is closed, and then what the pressure value is. Something that is interesting is there's some differences in, again, the two participants. The number of trials, I think, is around 25 per participant. I think we have 50 trials here, but I'm not actually sure about that. People take different strategies of how high they lift up the object. Not displayed here is the relative amount of time spent making contact with the object, but anecdotally, I'll just tell you that if you have haptics, what ends up happening is you spend more time grasping the object, you spend way less time transporting, which is interesting. And what else? Yeah. Something that's excited from the people who are making the comparisons between just the teleoperator performance is one of the side goals of the test was, yes, you want to bring the hacky sack from one side to the other. The secondary goal was try not to completely destroy it. So try to use as little pressure needed as possible. Of course, that's subjective. So that's one thing that we're looking at. What I'm going to show you instead is what happens when we train policies based on these two data sets. So what's happening here is the solid line is ground truth of what actually happened in the demonstrations. And these are rollout predictions for, we had a 2-second horizon for what the prediction would be. And these are all very noisy. Given pressure data, there are differences in when, say, the robot thinks it should lift off. And if you have pressure correspondence, without haptics, so it doesn't actually have this information. Without haptics, it lifts off curly much more often than the other one.
So on the left, so both policy, they don't have observation on the pressure.
This one, with haptics, the robot has observation, the human does not. And then, sorry. No haptics. The robot has pressure observation every time.
Okay.
The human does not get this information here.
Okay.
The human does get information here.
Okay. So, but both robots have the pressure observation. Okay.
And the question is, do they use it?
Okay.
I can't tell you for sure because I don't know. You got this basically at the same time that I got this. But these are some interesting differences between the two data sets. You do raise a good point. We were curious what happens in, so what we did was give the robot policy 0 pressure. So ablate it. And this is still somewhat noisy data, but something that we're interested in is, okay, so now in this ablation, you have a policy that expects to use, that we would expect, it would use pressure data, now it doesn't have it. What does it do? Compared to this one, where it shouldn't make any difference, because it wouldn't have this information any. Or sorry, the human wouldn't have this information anymore. So I don't really know how to interpret this right now, but it's interesting to know when the robot decides to lift off versus slam the object into the table. We don't really know what to make of this, but the goal for this is, here are some. This is a 3D trajectory of from start state to end state and how it deviates from the ground truth. Show the gray lines. One thing that we want to do with this information is then have online execution on the real robot and see what it does, but we haven't gotten there yet. Another thing that we want to look at is, all right, in this example that I showed you with the very preliminary data, we have the human having visual access to the task space. One thing that we collected but we haven't processed yet is an example where a human has the same camera view, or sorry, has no depth perception. So this is the wrist mounted camera on the robotic gripper on the nearby. And so if the human has to rely on, or will the human rely more on haptic information to figure out if they make contact with the object, if you have depth perception? And then also, what does that do for your demonstration behavior? Okay. Very preliminary work. But robots are using some form of the pressure information when the demonstrators are using haptic feedback. There's a difference. We don't really know what to do with it yet. And the idea is, well, if you have force feedback, maybe you're paying less attention to watching the visual deformation of the hacky sack. Maybe you have redundant information and you can have greater confidence. But this is very preliminary. What we want to do is do more ablations and figure out what's actually going on, and then stream the weights for getting sensory attention. What I have open discussion questions for you. If humans are exhibiting sensory density. We talked a little bit about this for the spider stuff. Are we using are our current architectures like efficiently supporting this, or should we think about different ways to encourage redundancy from sensor fusion? And then this is very broad. I just want to know, like, why do robots need so many demonstrations for a task in order to learn something?
This is actually the first question is actually the question I asked Jingzhou on his previous work.
Yeah.
So that like so transformer, it like naturally does have this like attention mechanism, but why if we just like scale, get more data, can transformer just address this like attention between sensing modalities? I don't have a good answer, but
I don't think anyone has good. I think that's one of the big open questions for robotics. I'm just hoping that DexLab has the answer and is hiding it from us. Okay, I'm just as stumped as you are. A secondary thought I had was, so thinking about transformers and attention mechanisms, we're hard coding this in the architecture. We're providing the attention mechanism. I wonder, is it possible, feasible, already done, something like that, of dynamically prioritizing attention mechanisms? Like, can there be a hierarchy of, okay, now we need an attention mechanism here between these two sensing modalities? Is it at the sensor level, or is it in some middle part of the model? Encoder, decoder, set.
I think the dynamic weighting is very important. Yeah, because the tactile, for example, I'm talking with you. I didn't use my skin and other modality to use it. So I feel like in manipulation task, there are a lot of stages. For example, the rate shot. For example, when moving to the object, transition stage, I think the visual is totally enough. But after contact, I think we need to use more tactile. I think there is also a very interesting paper. The name is like force touch begin when vision end from the Pinto, if I remember correctly.
Was that the new one? The
Uh,
one from like 2 weeks ago?
No, it's this year.
Oh, this year.
Yeah.
Okay.
So they are trying to figure it out when to use tactile and how to use tactile. I think, yeah, this is a very good question.
Is that the one with grasping strawberries? Gentle grasping? Or is that a different one?
I know one.
That came out and I have not read it, but it's on my, I need to read this.
Maybe it's.
Yeah, I think a lot of people are, now that tactile sensors are becoming
Oh, the name is
hardware
actually being-
available, I think a lot of people are figuring out what to use them and why the robots aren't using it. Okay. Am I out of time?
I think you're good, yeah.
Okay, then great. We won't get into that next section. But yeah, I'm curious about, yeah, if you take a robot and you're making all these observations, how do you translate like the robot senses? How do you translate experiences into robot experiences? And things like that. So, thank you for a really good discussion.
Thank you so much.